Hi, my name is Cody Deakins. I'm here to introduce you to ISGLIP, the Interstellar Solar Gravitational Lens Imaging Probe. So the problem that we're faced with is that the scientific community needs a new interstellar platform. That's because every human-made object or experiment that has reached there already is over 40 years old at this point. The unique data opportunities lie beyond that barrier, and the best way to learn about interstellar space is to go there. So to accomplish our goal, we aim to deliver a 50-kilogram scientific payload to interstellar space within 20 years. Interstellar space is defined as past 121 astronomical units away from the sun, at which point you cross something called the heliosphere. This is a lofty goal, as Voyager 1 was only able to accomplish this within 35 years, so we're aiming for nearly half of that. We also want to communicate data with Earth for up to 20 years after we continue on into interstellar space so that we can continue to communicate that data and keep providing scientific value. We also want to use our distance from the sun to analyze exoplanets using the sun's gravitational lensing, which is something that can only be done out there and was recently outlined in a publication. So the method that was proposed in that paper is something called solar gravitational imaging, and it relies on something called an Einstein ring. An Einstein ring is something that we observe behind large mass objects such as galaxies or stars, in which they basically bend and amplify the light behind them into a ring around them. And it actually turns out that at a distance of 650 astronomical units away from the sun, using a telescope of about 1 meter, the paper suggests that we could get observations of exoplanets and actual images of them with resolutions in the tens of kilometers. And that's something that is far beyond what we can currently do. We can also search those exoplanets and analyze them for signs of habitability, as well as their atmospheric makeup, their orbital periods, and rotational periods. So to accomplish our goal of reaching the heliopause within 20 years, we decided to go with an experimental option called the direct fusion drive. It uses the same fuel through the process of fusion to produce both propulsion and power for our spacecraft, which is important because at the distance that we're going away from the sun, due to the inverse square law, solar generation for power doesn't really work that well, or kind of at all. So it actually provides enough propulsion to reach the heliopause for ISGLIP within 13 years, which is insanely impressive. Our project lifecycle does take into account developing technologies like this, as we estimate a technological readiness level of 2. So there is still some research and development that goes into this. However, we do believe it is imperative to accomplishing our mission goals.
So my name is Liam Desai, and I will be demonstrating the initial sketch and the ConOps for ISGLIP. So the main component of ISGLIP is the actual satellite itself, and here in this slide you can see that there is several main components to the overall probe. First, there's the antenna array. These are represented by number 1 on the slide. And there's the fusion drive itself, which is number 2. The nozzle for the engine is 3. The experiment bay is number 4. You can see the doors are fully open there, allowing the experimental apparatus to be exposed to the interstellar space environment. There's the telescope, which is an infrared telescope. This will be the telescope used to look at exoplanets in the distance. And finally, we have the main satellite bus. A lot of these support systems and overall structural elements are housed in the bus. So next we're going to move right into the ConOps, and this is going to give an overall understanding as to what ISGLIP is and what it does, and why our proposal is the best one. So for starters, the overall mission is to have a spacecraft go into interstellar space. This has never been done in the sense that there has never been a space mission with the sole intention and sole mission of interstellar space travel. And it should be noted that for ISGLIP, this is also not the case. There is not the sole mission of interstellar travel, although that is the primary mission. The really exciting part of ISGLIP is the ability to have the secondary mission. The secondary mission, of course, is the exoplanet exploration idea. And our exoplanet exploration and imaging using the Einstein ring at 650 astronomical units on the way to the final interstellar destination is a game changer. It will allow scientists and engineers to have access to information they've never had access to before, and it will prove inconsequential when determining and talking about future interstellar space research and travel. As you can see, there's just a basic overall mission layout. So we have a spacecraft launching from Earth, a gravity assist around the sun. There's a gravitational lensing secondary mission. That's the mission I was just talking about. And finally, there's the interstellar space mission primary mission. And these will be using the tools housed in the experiment bay, such as sampling devices, radio antennas, and everything like that, just so we can better understand what the interstellar space environment is like. This is a more detailed look at the secondary mission. So as you can see here, we have a mock-up of what ISGLIP would be like, and it is staring at a region of interstellar space. The region where the Einstein ring is at, around 650 astronomical units, will allow ISGLIP to capture high-resolution pictures of distant exoplanets and stars, and possibly even their moons. So this is a very exciting development and very exciting part of our overall mission that is a game changer and really sets us apart from the competition.
Hi, my name is Dylan Preston. Taking a look at our subsystems overview, we can see that we are including a cosmic ray subsystem, plasma spectrometer, and radio science system, all different electromagnetic measurement tools used in the Voyager mission. Additionally, we're planning on including an infrared imaging system specifically tailored for our gravitational lensing imaging objectives. Further, the direct fusion drive is capable of producing 200 kilowatts of electrical power, which is more than enough for our different subsystems and electronics. Additionally, the direct fusion drive's aneutronic design will limit the amount of shielding we need to protect our subsystems from radiation. Taking a look at our timeline analysis, we can see that the majority of the mission takes place in this far interstellar and near interstellar region. There's over 20 years where data can be collected and sent back towards Earth, which means tons of different experiments will be able to be conducted. Additionally, it will take about 12 years to reach near interstellar, and then about 20 years to reach far interstellar using the direct fusion drive. And in that 20-year, or in that far interstellar region is where the gravitational lens imaging will take place. Now, more about the data that we're collecting. ISGLIP will bring back value that other teams cannot through our generation-defining gravitational lensing imaging. Specifically, Georgia Tech plans on applying image processing techniques to look for signs of life and infrastructure. MIT plans on assessing data collected on exoplanet composition, size, and position to update existing models. And Caltech plans on applying data filtration techniques to update and improve the resolution of ISGLIP over time.
Hey everyone, my name is Kian Zarboff and I'll be explaining the baseline cost analysis for this project. For now, our total set budget is around $8 billion. This may seem like a pretty high value for our mission goals. However, we first derived this overall 8 billion mark from the previous Voyager mission costs, which were around $895,000 in 1972. With inflation of the US dollar, we found it to be around $6.2 billion. And with the extra allotments in terms of propulsion technology and communication developments we plan to do, we upped that value to $8 billion to have margin for all the developmental tasks we need to complete. Although this is a pretty big number, we could say safely that if distributed across all American taxpayers, each taxpayer would be only responsible for $54 towards this mission, which in retrospect doesn't seem like a lot for the whole team. Looking down at this breakdown of our $8 billion goal, we start off with the fusion drive, which is our main power source and propulsion system. A really important, innovative system that will help us get to interstellar space. Additionally, we are allotting $1 billion towards the development of a better communication system by upgrading the Deep Space Network, a legacy system used by Voyager. And we have $1 billion each set aside for some scientific instruments development, the gravity lensing, as well as the overall structure of the vehicle and its power distribution systems. On the operations side, we have $2 billion allotted to our launch vehicle that will propel us into the stars, and we have $1 billion set towards the ground station operations, currently set in place to operate the vehicle and sustain data transmission throughout its mission life. Now, $8 billion is a pretty large sum to be asking of the American government and US taxpayers. However, we believe the benefits and the research and scientific data we collect from this mission will benefit mankind and the scientific research community greatly. Now, with this current design, no previous vehicle or existing design can match it in its ability to photograph deep space images and as well as travel in deep space and achieve target distances at this current state. Our imaging will be on the kilometer resolution, never been done before, and we will be able to reach the end of the heliosphere at a pace that no other vehicle can achieve currently. In addition, the internal development of the deep space network will benefit the future of many other space missions that require communication extensively deep into space. And when creating a comparison to different projects that are already funded by the US government, we can compare it to Lockheed Martin's current mission budget for the F-35 fighter jet being worth at around $398 billion in comparison to what we will be bringing to the table for the scientific research community. I believe our budget is very much justified.